Hey guys, Mr. McKinney here doing part 3 of our concavity and POI video series. So we're going to do an example using trig. So to find all extrema and POIs for the function sine of x minus cosine x on the interval 0 to 2 pi, including 0, not including 2 pi. Again, when we refer to extrema, we're talking about maxes and mins, and we're talking about both the local and the absolute. And local and relative mean the same thing. We talk about POIs, that stands for points of inflection. Extrema, we're going to be looking at the first derivative to find that. POIs, we're going to be looking at the second derivative. And in both cases, we're either looking for when it's 0 or undefined. And on a function dealing with sine and cosine, those are defined everywhere. So we're going to be looking where the first derivative is 0 and where the second derivative is 0. So the first thing we have to do is find the first and second derivative. So the first derivative of sine, is cosine. Derivative of cosine is negative sine, so that double negative is going to change the sign. And then the second derivative, the derivative of cosine, would be negative sine of x, and then the derivative of sine is cosine of x. So I need to know when the first derivative is equal to 0 and when the second derivative is equal to 0. So extrema, or at least possible extrema, happen when the first derivative is 0. So when cosine of x plus sine of x is equal to 0. Now you can think about when cosine and sine are the same value, except one's positive and one's negative, to think about how to solve this. Or you can subtract one over to the other side, so we can make it sine of x equals negative cosine of x. If I divide both sides by cosine, I can make it sine of x over cosine of x equals negative 1. And then sine divided by cosine is the same as tangent. And I want to know when tangent of x is equal to negative 1. Tangent of x is equal to negative 1 when x is equal to 3 pi over 4 and 7 pi over 4. And then we're going to do the same idea for the second derivative. Find out when the second derivative is equal to 0. That's going to give me my possible POIs. And again, these are critical values. Critical values are another name for possible extrema. Actually, critical values are the x values that go with critical points, and critical points are where you would have the possible extrema, because the extrema are going to be the y values that go with these critical x values. All right, so again, for points of inflection, that's when the second derivative is equal to 0. So the second derivative was negative sine of x plus cosine of x. Again, you can think about when sine and cosine have the same value, and this time, since sine's already negative, they would cancel out. Just think about it on the unit circle that way. Or you can subtract the cosine over, so negative sine x equals negative cosine of x. Divide both sides by negative cosine. So that's going to give you a positive 1. Negatives cancel out and give us a positive tangent of x. So x would be the inverse tangent of positive 1, which is going to happen at pi over 4 and 5 pi over 4. Again, these are on the interval from 0 to 2 pi. Otherwise, these are just going to keep happening over and over again every pi. Okay, so the possible POIs happen when x is pi over 4 or 5 pi over 4, because that's when the second derivative is equal to 0. The possible extrema, which are also known as critical values or critical points, critical values when they're just x values, critical points if I found the y values by using the original function. Those happen when the first derivative is 0. All right, now let's put it all on a table and organize that information. So in my table, I'm going to put my x values at the endpoints, and then I'm going to put all the x values that I found in order. So pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And I want to leave a little bit of space in between each one. Now for the first derivative, we found out that the first derivative was 0 at these two x values. The second derivative was 0 at these two x values. So that's the first thing that you should fill in. Then you're going to go to the first derivative and you're going to figure out whether it's positive or negative on each side. So for example, if I plug in 0, cosine of 0 is 1, sine of 0 is 0, so that's a positive value. So we're going to have positives here. If I plug in like pi, cosine of pi would be negative 1, sine of pi is 0. So we've got a negative value until we hit 0 again. And then if I plug in like 2 pi, it's the same as 0. So we're at positives. So this would tell me where I would have a local max. This would also tell me where I would have a local min. Now those might also be the absolute max and min. I'm going to have to check them against the endpoints. Now for the second derivative, I'm going to plug in like 0. Sine of 0 again is 0. Cosine of 0 is 1. So we're getting a positive value. And then we're getting a negative value. And then we're getting a positive value. And this would be if I plug in, let's say, pi into here, I would get a negative value. And then if I plug in 2 pi, I'd get a positive value. Since the second derivative does change, I do have a POI here, and I do have a POI here. So I have points of inflection, I have local maxes and mins, and I would have to fill in these f of x values to figure out the local max and min and compare them against the endpoints. So if I do f of 0, I would get negative 1. If I plug in, because now I'm plugging in 0 into this original function. If I plug in 3 pi over 4 into the original function, I would get root 2. If I plug in 7 pi over 4 into the original function, I would get negative root 2. And then if I plug 2 pi into the original function, I would get negative 1. And you have to check this endpoint even though it wasn't included, because that might make one of these either be the absolute max or min or not, depending on whether this value was above or below it. Since it ends up being in between our local max and min, it ends up not mattering on this problem, but you still always need to get in the habit of checking both endpoints. So since root 2 is greater than my endpoints, this is a local max. It's also the absolute max. So the local max and the absolute max are both root 2. And then since negative root 2 is less than my endpoints, then we have a local and absolute min of negative root 2. So summarize that information here. Oh, again, you have POIs down here where the second derivative changed sign. All right, let's do a whiteboard problem, and let's assume that we're dealing with position here, and then we're going to talk about what that's going to mean when we have our velocity and acceleration. So position using this time. So find the first derivative, second derivative, figure out where they're equal to 0, and then fill in the table. So go ahead and hit pause and try to see how you do. Okay, let's see how you did. So first derivative, should have gotten that the velocity was 3t squared minus 18t. Second derivative, should have gotten 6t minus 18, which is the acceleration. Now we can see that the first derivative is 0 when t is 0 and 6. The second derivative is 0 when t is 3. So 0, 6, 3, and then my two endpoints are the values that need to go into my table. So those were the x values. We knew that the first derivative was 0 for 0 and 6. We knew the second derivative was 0 for t equals 3. We had to check these values. You really don't need to check this value to see if it's a max or a min. You have to check this value to find your POI. So your POI would be at 3, negative 270. Since your first derivative goes from positive to negative here, you have a local max. Since your first derivative goes from negative to positive here, you have a local min. And this is the local max or local min of position. So when the velocity is 0, that tells you where you have a local max on position or a local min on position, depending on what the velocity did. And again, the second derivative shows you acceleration. Now, a common question is, when are you either speeding up or when are you slowing down? And again, remember, we're speeding up when velocity and acceleration have the same sign, and we're slowing down when velocity and acceleration have different signs. So a table like this will help you answer that question also. We're speeding up when we have the same signs. So same signs here and same signs here. So we'd be speeding up on the intervals 0 to 3, and then again from 6 to 10. Just always do open intervals. And we're slowing down when they're different. So we'll change colors. We'll go to green real quick. So when velocity and acceleration are different, we're slowing down. So a positive velocity with a negative acceleration is slowing down. Or a negative velocity with a positive acceleration is slowing down. So between 3 and 6, we're slowing down. All right, that says -5 to 0. All right, so again, to find where the original function is increasing or decreasing, you look at the first derivative. To find out where the original function is concave up or concave down, so that's when you're looking at the second derivative. If it's negative, it's concave down. If it's positive, it's concave up. That says concave. C-O-N-C-A-V-E. All right, hope this was helpful. Reach out to your instructors if you have questions, and we're going to go over some like this in class as well. Again, if you haven't put this in your notes yet, to me this is the most important part from this chapter. Understanding what this table means will help you answer a lot of questions. So when you're asked about extrema, you're talking about maxes or mins. You're looking at the first derivative. When it's 0 or undefined, that'll tell you where the critical points are. And if the first derivative changes sign, either positive to negative or negative to positive, that's where you're going to have a max or a min. The first derivative also tells you, this is just a side note, but first derivative will tell you increasing or decreasing about the original function. So if the first derivative is positive, then f of x is increasing. If the first derivative is negative, then f of x is decreasing. Same idea for concavity. If the second derivative is 0, or if it's not defined, or doesn't exist, then that's a possible point of inflection. If the second derivative actually changes sign, then that's an actual point of inflection. So if the second derivative goes positive to negative or negative to positive. So the first derivative tells you if the original function is increasing or decreasing. The second derivative being positive or negative, second derivative being positive or negative tells you if the original function is concave up or concave down, because it's telling you if the slope is increasing or if the slope is decreasing. And everything, the relationship between f and f prime is the same as the relationship between f prime and f double prime. I'll come back to that later in the course, but if you just let that start to simmer in your brain. So when we think about, let's see if we can get to a blank. No, all right. When we think about the relationship between f and f prime of x, that's the same relationship as the relationship between f prime and f double prime of x. So if you have questions relating velocity and acceleration, those are the same types of questions that can be related with position and velocity. Again, this is all kind of a side note, so these last 2 minutes of this video you can kind of ignore. Or maybe watch it again in a couple of weeks or a couple of months and it might make more sense. All right, hope this was helpful. Reach out if you have questions.